So today let's take a look at this questionable 2-in-1 USB charger. It has basically two functions. It can charge your USB devices from mains, or it can also charge them from your car. And of course this part of it looks quite questionable, because what if you plug it in mains, remove this and touch this? And it was donated to me by a viewer, so thank you, and it definitely looks quite interesting. So let's take a closer look at it. Here is the mains input with a European plug. Here is the car input, which goes into the cigarette lighter socket. Here is the USB output, an indication LED here, and here is the label. It says 2-in-1 charger, and the first input is 100 to 240 volts, 50 or 60 Hz, which is basically a universal mains. And the other input is 12 to 24 volts, which is any vehicle, a car, truck, bus. And the output is what? From 4 to 8 volts? 1000 milliamps. So is the output voltage really anything from 4 to 8 volts? It's a USB. A USB port should have 5 volts nominal in it, plus 0.25 minus 0.6 volt, which ranges from 4.4 to 5.25 volts. If it can really be 8 volts, it can easily destroy your devices. So let's try to test it using my USB meter. Let's plug it in. The LED comes on with no explosion, and the voltage is 5.16, which is quite okay for a USB. Let's try to load it. 1 amp. Well, it's just half an amp, and the voltage already falls to 3.4 volts, which is definitely too low for a USB. So as you can see, it says 1000 milliamps, which is 1 amp, but it can't even supply half an amp. When I try to load it even more, it just completely dies. Now let's try to load it a little bit less, using a higher resistance resistor, and it supplies 0.36 amps, and the voltage is still too low for a USB. It's just about 4 volts. Now let's try to load it even less, adding some resistors in series, so it's a higher resistance. And now the voltage is just about the minimum voltage of a USB, and it supplies 0.23 amps. So this is the maximum current it can supply without dropping the voltage below the minimum of a USB. This is what they call 1 amp. And I should probably try to run it a little bit longer, having my fire extinguisher ready, of course, but before I do this, I should probably test the 12 volt input of it, because I can already smell something burning, so before I test it for a bit longer, I have to test this 12 volt input, because it can otherwise blow up and I would have no chance of testing it, and the battery in my camera just ran flat. And let's test it like this, if it's isolated from a mains. It seems to be isolated, and what about the USB port? It also seems to be isolated. Now let's try to measure the leakage current using my multimeter and a lamp in series for the case of short circuit. And there is no leakage here, no leakage, no leakage, no leakage here, and if I turn it around, no leakage, no leakage, no leakage, no leakage, no leakage. So it seems to be okay, there is no leakage current, but still, it doesn't say anything about the reliability of the isolation in it, of course. Now let's try to test it using 12 volts, to see if it can run in a car. So this is about 12 volts, and let's try to test it. Let's also measure the current it draws using my clamp meter, set it to DC, zero it out, and let's try to connect it to it. Now it's loaded with a resistor. It doesn't blow up, it does something, it lights up. Now let's measure the current using my USB tester. It draws about 0.2 amps from 12 volts and it supplies 5 volts, 0.3 amp. It seems to work better on 12 volts. Let's try to load it more. Now I draw about 0.4 amps from it and it's still about 5 volts. Let's try even more resistors, even more load. And at 0.65 amps, the voltage is already too low. So let's go back a tiny bit, and at about 0.6 amps, the voltage is still fine. 4.8, 9, it draws 0.43 amps from 12.2 volts. So 0.6 amps is the maximum current when it runs on 12 volts. Now let's try to calculate the efficiency of it. So the output power was P equals U times I, and this is the voltage, it's about 4.8 volts times the current, which was about 0.61 amps, and this is 4.8 times 0.61 is 2.92 watts. And the input power was the input voltage times the input current, and this is 5.11 watts. And the efficiency of it is the output power divided by the input power. And this is 0.57 or 57%. Such efficiency at a full load is definitely not much. And at a lighter load, 0.27 amps, it's even worse. The efficiency is less than half. But as you can see, the input current is lower than the output current, which means that it's not a linear regulator. It has to be a switching regulator, probably a buck regulator. Now let's try to run it a bit longer to see what happens. So the power supply ran for about 2 hours with no explosion, which is nice, but I can smell something like a hot circuit board. And now let's take a look in it. It probably has just one screw under this sticker. Yes. Let's unscrew it. And this one is also screwable probably. Yes, and there is a fuse in it, which is a luxury. And now it falls apart. So here you can see the internals of it. Is it interesting? So here you can see the board. This is probably the mains input. Just a single diode rectifier, probably an inrush resistor, the main primary smoothing capacitor, probably some startup resistor, current sensing resistor, the main switching transistor here, some auxiliary transistor, auxiliary capacitor, some interference capacitor, some diode, maybe in a snubber network. On the secondary side, there is the filtering capacitor and the rectification diode, the LED for indication, and for the car input, there is probably a buck regulator with this chip and this inductor. And there is also some diode and capacitor in the buck regulator, another diode here. There is quite a lot of diodes on the secondary side for some reason. And some resistor probably in some voltage feedback of the buck regulator, and here's the output, the USB connector, which is a little bit rusted. That's nice. And of course here's the transformer of the switching power supply, and those two resistors look like a resistive divider setting the voltage of the buck regulator. And this charger apparently went through some cost cutting, because on the board there is a space for a bridge rectifier, but there is just a single diode. And there is also a space for an optocoupler, but there is none. And this primary smoothing capacitor is just 2.2 micro, which is not much, especially given that it's charged using just 1/2 cycle. Now let's take a look from the other side of the board. Are there any SMD components? Okay, I can see some. There are some SMD resistors and few capacitors. But it looks nice. The isolation distance on the board between the primary and secondary side is quite big. It looks like it could be up to a European standard. The isolation definitely looks much better than I expected. It surprised me. And this capacitor is not an interference capacitor between the primary and the secondary side. It's on the primary side and it's probably a snubber network. And there is no interference capacitor in between of the primary and the secondary side, and this is why I didn't measure any leakage current to ground. So it probably produces some interference. There is absolutely no interference filter and no interference capacitor in between of the primary and the secondary side, but it looks like there is a resistor in series with the mains, and if it's a fusible resistor which also works as a fuse, it's good, but if it's a normal resistor, it's not so good. So the fire safety of it depends on what type of resistor this is, and the electrical safety probably depends on just this transformer, because the isolation distance on the board is quite nice. There is no optocoupler and there is also no interference capacitor between the primary and secondary side. So this transformer is the only critical component for the electrical safety, and I will probably take a look inside of it later. So if this resistor is fusible and this transformer has a good isolation in it, it should be safe, but still, there is absolutely no interference filter, so interference-wise it's up to no standard, and also the current it can supply is not what it claims. So it's still not worth it. And it has a nicely rusted USB port. That's amazing, and I'm afraid that this resistor is not fusible, so the fire safety of it is questionable. It has a very nice fuse in the car input. Fast, 2 amps, 250 volts, but just a very questionable resistor in the mains input. The resistor looks just like the other resistors, so it's probably not fusible. But now let's try to draw a schematic of it. So here's the schematic of it, with my cat on it, of course. So the mains comes in, here's the single half cycle rectifier, the inrush resistor, which may or may not be a fusible resistor, but it's probably not. Here's the smoothing capacitor, which is a very low capacity, unfortunately, and the rest of it remains a secret. So here you can see the transformer and the primary circuitry. Here's the primary winding, the secondary winding, and the auxiliary winding. Here's the main switching transistor, which has a snubber network, which is a luxury here. And it's basically a self-oscillating circuitry with a feedback from the auxiliary winding. It has a startup resistor which supplies a small current into the base of this main transistor, so it partially turns on. It connects some voltage into the primary, so some voltage is induced in the auxiliary winding, and then it supplies more current into the base of this transistor through this feedback circuitry. So then the transistor turns on fully and it stays on until this capacitor discharges, then it turns off and it all repeats. It keeps oscillating because this is a positive feedback. When the transistor starts turning on, it will turn on fully, and when it starts turning off, it will turn off fully because of this feedback. So this circuitry is basically oscillating, and there is a current sensing resistor, and if the current is too high, the voltage drop of this resistor will also be higher, and it will be enough to turn this auxiliary transistor on. If the voltage drop of it is over about half a volt, this transistor will turn on and it will draw some current from this capacitor and discharge it faster, so the duty cycle will go down, basically. The time when this transistor is on will be shorter. Normally it's like, let's say this, and if this transistor draws some current from the capacitor, it discharges faster, so it reduces the duty cycle. So if the current is too high, it will reduce the duty cycle and keep the current at a safe level. And the voltage regulation works the same way, and it also shares the same auxiliary transistor. And it has no optocoupler, so it's not sensing the voltage here at the output, it's sensing the voltage on this capacitor, which is charged from this auxiliary winding via this diode. And it's a flyback switching power supply, which means that when this transistor is on, the diodes are not conducting. When this transistor is on, this winding has this polarity of a voltage, so the dot is negative. So also those dots are negative, and this diode is not conducting, and this one is also not conducting. So when the transistor is on, the energy goes into the transformer and it's stored in the ferrite core of it as a magnetic field. And when the transistor turns off, the polarity is suddenly the other way, and the energy from the transformer goes to the secondary side, and it goes like this, and it charges this capacitor via this diode, and it also charges this capacitor via this diode, like this. And the voltage on the windings is about proportional. It always has a certain voltage per certain number of turns. So the voltage on this capacitor is roughly proportional to the voltage of this capacitor. The voltages are not perfectly proportional because the coupling of those windings is not perfect, and there is also a variation of the voltage drop of those diodes according to the current through it, but it's roughly proportional, so the circuitry can roughly tell the voltage here by measuring the voltage here. And it simply senses the voltage on this capacitor using this Zener diode. If the voltage on this capacitor is enough, this Zener will start conducting, and it will pass some current into the base of this transistor, and it will draw some current from this capacitor, discharge it faster, and limit the duty cycle from this to this, for example. When you turn it on, it will run at a full duty cycle until this capacitor charges, and when it charges to the right voltage, about 5 volts, for a USB port, it will start limiting the duty cycle. Because if the voltage of this capacitor is high enough, also this capacitor will have a high enough voltage to pass some current through this Zener and start limiting the duty cycle. And of course also the charging current of this capacitor may be limited on the startup, because when the current is too high, it will sense it on this resistor and limit the duty cycle. And when you, for example, load the power supply more, the voltage on this capacitor tends to go down, but then the voltage on this capacitor also goes down and it passes less current through this Zener, or no current. So the duty cycle goes up and compensates for it, so it keeps this voltage at about 5 volts. But if you load it too much, it will sense the overcurrent on this resistor and limit the duty cycle, and the output voltage will drop to prevent a damage to the power supply. But the current it can supply is kind of too low, and it may also be because of this capacitor having a too low capacity, and also because just a single half cycle rectification. Because this is the main sine wave. If you rectify it using just one half cycle, you rectify it just here. But if you use a bridge rectifier, you rectify it in those 2 points. So now let's compare the single half cycle rectification with 2 half cycle rectification. So if you have a single half cycle rectification, it charges the capacitor just here, and then the capacitor discharges until getting to this half cycle, and then it all repeats, and the voltage falls quite low here. But if you have a full bridge rectification, you recharge the capacitor twice as often. So the capacitor discharges and recharges here, discharges, recharges here, discharges, and recharges here. So the voltage falls into this level, but in single half cycle rectifier, the voltage falls to this level, which is much lower. So as you can see, the single half-cycle rectification, which is the blue line, allows the voltage on this smoothing capacitor to fall much lower, and at this level, the voltage on this capacitor may not be enough for the power supply to operate properly, and it may be the reason why the current is so low at the output. And maybe also this current sensing resistor could have been a lower resistance, and this base resistor a lower resistance, and this capacitor a higher capacity, to get a higher current here. So this is the mains power supply section, and now let's take a look at the car power supply section, which basically uses a buck regulator with a very common chip, 34063. The chip has a power supply pin, ground pin, a feedback pin, oscillator pin, some output, some current sensing pin, and the switching transistor in it is probably here, like this. There is some auxiliary transistor here in it, which has the collector connected here, and this is the collector of the main transistor, and this is its emitter. And the base of this transistor goes into some control circuitry, and it's switching. It's a buck regulator, so it switches the positive power into here, and when it's off, the current goes through this Schottky diode. When the transistor is on, the current goes from the input through the transistor, the inductor into the output and back. And when the transistor is off, the current goes just from the inductor through this diode into the output. So it's recycling the energy accumulated in the inductor. And there is a resistive divider going into the feedback pin, setting the voltage, and the threshold voltage of this feedback pin is 1.25 volts. And this resistive divider is set such a way that when the output voltage is slightly over 5 volts, it gives 1.25 volts here, and then the chip starts limiting the duty cycle, so the voltage doesn't go up anymore. And there is also a Schottky diode, which prevents the current from the mains power supply from going back into the buck regulator. And the diode is dropping about half a volt, so the voltage here has to be about 5.5 volts. And the voltage sensing is connected after this diode, which means that the voltage drop of it is not affecting the nominal voltage. And here is the current sensing resistor of the buck regulator. So this power supply has a good isolation on the board between the primary and the secondary side, and it has a snubber network, which is a luxury for Chinese power supplies, but otherwise it's quite dodgy. This resistor is maybe fusible, maybe not, and the current capability is very low, especially when running on a mains voltage. And there is absolutely no interference filter in it. It was only able to supply 0.2 amps when running on a mains voltage. Can I improve it by increasing the capacity of this capacitor? Let's try to use 22 micro here. And that's it. Now let's test it, and of course it may also blow the inrush resistor. And of course the cat goes behind the door. So is it going to explode now? Let's test it. And yes, the inrush resistor just blown. So now the blown inrush resistor is bypassed, and let's try it again. It runs. Now let's try to load it. It's upside down, of course. 0.1 amps. 0.3 amps. Already too low voltage. So it seems like it doesn't help much. It can still supply just 0.2 amps before the voltage gets too low, so the problem is probably somewhere else. Maybe this current sensing resistor is too high, or this base resistor is too high, or this timing capacitor too low, or maybe this transformer is poorly designed and it's saturating and it's causing this current limit to kick in. So let's try to put another 10 ohm resistor in here in parallel, turning it into 5 ohms in total. So now the current sensing resistor is just 5 ohms, and this is the point when it probably blows up. Now the current limit threshold should double. So let's brace for explosion. It runs. Let's increase the load a little bit. Let's actually double the load. And it kind of supplies 0.3 amps, and the voltage is still just about right for USB. So now it can supply a little bit more, almost double the current. So as you can see, you can increase the current capability of it, even though nobody knows for how long. And it's still far from the 1 amp rating. Is the transistor hot? Not yet. It seems cool. So it seems to be improved, and the transistor doesn't even get hot. It's quite cool. But of course I don't know how much I can push the current limit before it blows up. What if I change this resistor in the base of the transistor? So now it's already horribly botched, and I accidentally broke some SMD capacitor, so I put another capacitor with the same capacity in it, and I will probably try to use another value of the capacitor anyway later. So now let's try to test it. I have put 560 ohms here. So this one is now 560 ohms, and let's see what happens. It runs 4.4 volt, 0.36 amps. Let's load it more. It's the same as before, because at a higher current, the voltage is already too low. Now let's try to change this capacitor to 22 nano. So the feedback capacitor now has double the capacity. Does it blow up? It doesn't. And the voltage is slightly higher now. Let's load it more. But the voltage goes down again. Well, it's almost the same. So it seems that those two components in the oscillator feedback don't have any effect on the current capability. Now let's try to put a diode in series with this Zener to increase its voltage drop, which may increase the output voltage. So the Zener diode has a diode in series now. So let's test it. No explosion and a higher voltage at the output. Let's try to load it more. And it supplies a higher current with the voltage still acceptable. That's nice. Let's load it even more. 0.7 amps, and the voltage is like almost acceptable for a USB. That's getting better. But when it's not loaded, isn't the voltage too high? Well, it is. Now the problem is that with no load, the voltage is too high, so adding this diode is not a solution. So let's go back and remove this diode, because otherwise the voltage with no load is too high. So it seems like the only way to increase the current is to reduce the resistance of this current sensing resistor. So let's reduce it even more. So this parallel resistor is going to be 4.7 ohms, which gives 3.2 ohms in total. So now the current sensing is 3.1 ohms. And now, of course, it absolutely has to blow up. It doesn't, and the voltage with no load is okay. So let's try to load it. 0.4 amps, still kind of nice voltage. Let's load it even more. And now the voltage is too low. So the maximum current I can get from it is about 0.4 amps. So it seems like you can double the current capability by halving the resistance of this current sensing resistor. And there is this strange resistor which probably helps to recharge this capacitor when this winding is negative, when the transistor is off. When this transistor is on, the current from the auxiliary winding goes through the base of this transistor like this and charges this capacitor in this polarity. But when the transistor is off, this resistor probably helps to charge this capacitor in the other polarity to prepare it for the next cycle. So let's try to replace this resistor with 15 kilo ohms. Or let's actually put 15 kilo ohms in parallel to it. This is just an extreme botch. What happens now? Does it explode? It doesn't, surprisingly. It runs, but can I load it more? It does improve, but very slightly. So it seems like 0.4 or 0.5 amps is the maximum I can get from it. I could get slightly more by increasing the voltage by putting this diode here, but then, without any load, the voltage is too much. Without any load, the voltage goes too high because the sensing of the voltage is here, not here. It's indirect. So the voltage tends to drop under the load. So this is probably enough of experiments. Even if I make it supply more current, the voltage without any load will be too high. Now let's take a look inside of the transformer. Let's open it quickly and take a look at the winding. And here's probably the auxiliary winding of it. It's on the primary side and it seems to be nicely isolated from the other windings. And it is 1, 14, 15, 16 turns. So it seems to be nicely isolated so far, and the winding didn't go to the edge, so it couldn't fall through the gap to the other windings. Because if the winding goes to the very edge of it, it can fall down and meet with the other windings, the turns of it on the sides. And here's the secondary, a thicker wire. 1, 2, 13, 14, 15. So it seems to be nicely isolated so far, but I can see some problem here. Here is the primary and the end of it here is sticking out. So the secondary can actually touch it here. This end of primary can come into contact with the secondary and this is not good. So this could be some safety issue, and now let's take a look at the primary. Under some isolation, it's again about 2 layers of isolation, and here's the primary of it. And the primary is 1, 2, 3, 4, 200, 201, 2, 3, 4, 5, 6. So here you can see the numbers of turns in it, and I have decided to completely remove the primary side and use just the buck regulator. The buck regulator actually looks nice, it works well. The only problem is that those 2 capacitors have a very low capacity, just 10 micro. And this is probably to make it cheaper and to use the same value for all those 3 capacitors. It's not necessary to use a 50-volt capacitor when there is just 5.5 volts. It could be a lower voltage rating but a higher capacity. But because I removed the main part of it, I can short out this diode. So this capacitor is now in parallel to this capacitor, and I can also replace this one with a higher capacity. And bypassing this diode improves the efficiency because there is no voltage drop anymore. So let's put a 100 micro 50 volt capacitor here. So here you can see the modified board. And now let's test it. And it seems to work at 12 volts input. 0.4 amps, let's load it more. 0.6 amps, okay. And 0.7 amps almost, and it seems to be too much. So about 0.6 amps is okay. It's not 1 amp, but still good. I could probably increase it by reducing the resistance of this current sensing resistor. And is it any better with a 24 volt input? Let's try it now. Actually, it's still the same. The input voltage doesn't change the output current capability. Let's try to reduce the resistance of this. So now this resistor is 0.2 ohms. Does it supply any more current? 0.6 amps, the voltage is still fine. And close to 0.7 amps, and the voltage is too low. So the current doesn't go any higher. Now let's try to see the buck regulator on my oscilloscope. And of course I forgot the input voltage and the input current. So you can calculate the efficiency yourself. This is at 12 volts. And this is at 24 volts. So the ground of the oscilloscope goes here, of course, and one channel goes to the output of the chip here, and the other channel will go to the input voltage, output voltage, and probably this current sensing resistor. So here you can see it on the oscilloscope. The time base is 5 microseconds per division, and the first channel is the output of the chip, which is switching, so it's a nice square wave. 5 volts per division. Actually 0.5 and times 10 probe. The probes are set to times 10 using this switch on it. The period of the signal is about 2 divisions or 10 microseconds, so the frequency should be about 100 kHz. Let's try to zoom it a little bit. Now it's 2 microseconds per division and it's 5 divisions, so it's still 10 microseconds or 100 kHz. And here you can see the ripple at the output. It's 10 millivolts per division and times 10 probe. So it's 100 millivolts per division, and it's now 1 division, which means about 100 millivolts peak-to-peak ripple at the output. And of course, to measure the ripple, I have to set it to AC only for this channel. And now here you can see the ripple at the input. Because it draws the current from the power supply in pulses, it causes some ripple to go back into the power supply. And this is the reason why the input capacitor has to have a high capacity. And it also should have a low internal series resistance and inductance, which my capacitor probably doesn't have. And finally, here's the voltage on the current sensing resistor. When the chip is off, there is no current in the resistor, so there is no voltage drop on it. And when the chip is on, the current gradually goes up in the inductor as the energy builds up in its ferrite core in a form of magnetic field. And of course, when I increase the input voltage, the amplitude will go up and the duty cycle will go down as a compensation to keep the output voltage constant. So this is Teardown, and see you in my next videos, and thanks to all of my patrons on Patreon. I really appreciate your support.